Hello everyone. In this video, I want to try to teach you a little bit about reflection and the part of optics that deal just with reflection. What happens in reflection is that light hits a surface. Everyone knows that. But when light hits a surface, that energy that light contains or transmits, when it strikes the surface, some of that light is absorbed and some of it is re-emitted. So when you have reflection, it depends on the type of surface you hit, whether you get all of that light or energy reflected, or some of it is transmitted, or a mixture of transmitted and absorbance. A lot of that depends on the surface of the material that you're striking. In the ACDAC packet, it uses the words specular reflection, or diffuse reflection. So specular reflection is just a weird word. Most people just call it or just think of it as the reflection that you're used to. That's when the surface is very smooth, so virtually all the light energy that strikes the surface gets reflected back. So that's specular. I think of it as just regular old reflection. And then you have diffuse reflection. That happens when the surface that you strike is kind of rough. You need to really look at a picture of this, and I don't have one in this particular PowerPoint, but when a light hits a rough surface, the angles that it gets reflected at are really tight, and they don't come back at the same angles, so you don't get as full an image or as much of the energy coming back when you have this diffuse reflection. So just think of diffuse reflection as being from a rough surface. Okay, when we deal with reflection, the most important thing is the law of reflection. You see that on the screen. It says the angle of incidence, which is the incoming light, equals the angle of reflection, which is the outgoing reflection light. Now, to understand all this, we need to understand a couple of the vocab words here, and that'll be important moving forward for refraction as well. So the incident ray here, I'm highlighting with my cursor, is the incoming. So you start getting used to the word incident as meaning incoming, and then reflection is outgoing. A very important part of understanding all this is the normal. This is the red line here I'm showing with my cursor. The normal to something is always perpendicular to the surface. And so when we take angles for these light rays, both incident and reflected, we always take the angle from the normal position, not the surface. So get used to doing that. I remember that was a little tricky when I first started learning mirrors. The law of reflection really works best for flat mirrors and plane surfaces only. That just means a flat mirror. And of course, it's also going to work best for specular reflection. So we don't have rough surfaces, really, we don't get true law of reflection. So just once again highlighting there's a normal, and that's going to be very important for you. All right, so I remember when I first learned mirrors, I was always kind of, I don't know, put off or confused by the word or the usage of plane mirror. I guess maybe in my young mind I always thought I used the wrong meaning of plane. I thought it was just like regular plane, like ordinary. But what we mean here is a flat mirror. I don't know why they don't just call it a flat mirror, but they don't. They call it a plane mirror. So one thing we know from our experience is that when you put an object in front of a flat mirror, you see an image. And that image is virtual. It's not really there. And that's all another vocab word that we're going to be seeing more and more as we go through mirrors and lenses. Virtual images look like they're really there, but they are not really there. We'll talk more about that in a moment. But also notice when you put an image in front of a plane mirror, the virtual image that you see is always an equal distance, it seems, behind the mirrors. And they also have the same heights. So in a plane mirror, you basically see the same thing. It's just a virtual image, and we know that it gets inverted on the horizontal axis. All right, so the virtual image thing is weird enough, in my opinion, to just talk about it for a second. A mirror or an image that is virtual can't be projected onto a screen. So it's not like a hologram I know that's what I thought when I first heard the word virtual, like it's like a hologram, something that you project. It's just not real, but it looks real. No, a virtual image can't physically be projected onto a screen. A real image would show up if you were to put it on a movie screen, for example. So virtual images the only way you can test them is to light them up and make sure that it can be projected on a screen. So I have a couple of pictures here on the screen, and you just kind of got to think outside the box on this one a little bit. I have the picture of the woman here looking in the mirror. Of course, her image shows up to her. Now, you got to kind of leave her real face in place and just look at the image that's produced. And would that image show up on a screen like by producing its own light, if you will? Could it project itself onto a screen? And the answer is no, it wouldn't show up on the screen. So therefore, it is a virtual image. So real images, of course, are the opposite. Those ones you can project on a screen. And for mirrors, you'll always get a real image on the same side as the object that you're getting the reflection of. Virtual images will always be on the opposite side. In addition to real versus virtual, some other characteristics of images of objects that we get from looking in a mirror are the size of the object. Does it get enlarged, magnified, or does it get reduced? Position, so is it on the same side or is it opposite side, whether it's virtual or not? Is it same side or opposite side? And the orientation, so does the image come back straight up and down, or does it get flipped upside down? So those are things we always look for. For flat mirrors, it's pretty simple. I'll go back to the original thing here. For flat mirrors, we always get a virtual image, always the same distance behind the mirror as in front, and the heights are the same as well. Other types of mirrors can be spherical. There's lots of types. We're just going to talk about spherical. That's the only thing that's mentioned in the reading. So concave and convex. Hopefully these are terms that you've seen before. Convex mirrors are called diverging, concave are called converging. I don't really have a good memory device for that, so just focus on learning which is which. We'll start talking about convex mirrors. You will see these mirrors on like you see in the picture here on the corners of streets so people can see what's coming. These mirrors curve outward, and then they always produce smaller images that are virtual, always. Other places you see these, rear view mirrors, store security. So next time you're in a convenience store, try to find the convex mirror. Use this in a corner somewhere up high so that the cashier can look at people as they're perusing the aisles and making sure they don't shoplift. So they always give you reduced images that are virtual. The other type is called a concave mirror. Now this one was easier for me to remember because it looked like it had caved in. So concaved, it has the indentation in the middle. So as you can see from the picture here, this is a very important illustration. When light rays strike a concave mirror, they get reflected, and they get reflected at some point. All the rays go through a certain point, and that is called the focus. Every spherical mirror can do this, and so for these type of mirrors, we call it a focal point. You can't be too close or it doesn't work, but if you get it a reasonable distance away, you have a focal point. Well, just like the law of reflection slide that we had at the very beginning, we need to hit some vocab words here to understand how we're going to use this. So we talked about the focal point. It's always a certain distance in front of the mirror, and that distance just depends on the curve of the mirror itself. So there's a radius, there's a fixed distance there depending on the curve. So we call that the center of curvature, the distance from the surface of the mirror twice the, so the center of curvature is the radius of the center of this imaginary circle to the surface of the mirror. The longer the center of curvature, the sharper the curve of the mirror. All right, so we have that focal length is the distance from the surface to the focus, that focal point. And very importantly, we have this thing called the principal axis. I'm circling it now with my cursor. This is a line directly through the middle, through the center of curvature, and through the very center of the surface of the mirror. Okay, so we're going to do everything in reference to that principal axis here. It's kind of like the normal that I showed you in reference to the law of reflection. All right, little equation here. The center of curvature, if you didn't hear me say it a moment ago, is always twice the focal length. So if we know one or the other of those two things, we can simply solve for the one we're missing. All right, to work with these mirrors, we're going to use a ray diagram. I know for a fact most of the time you take multiple choice tests, they're not going to make you draw these ray diagrams. So even though we may not be doing that, it's a good practice to go through one just so you can kind of see how this all works out. So let's do an example here. I have a principal axis and I have a concave mirror. And I've just put my center of curvature, my focal point in there. And now I'm going to put my object. So I'm going to let this arrow represent my object. And if we were doing this on paper, we would really want to take a ruler out and do everything to scale, and it gives you tremendously accurate results. I remember last time I did this in college, it works really well. So to draw this, we're going to always, from the very top of our object, draw a line over, just directly over, straight to the surface of the mirror, and we're going to reflect off through the focal point. So you would just take your ruler, draw it over and down through the focal point. So that's ray number 1. Rule number 2, you're going to take a ray from the top and you're going to go through the focal point. Okay, so it's going to strike the surface of the mirror after that, and now you're going to reflect off parallel, like that. Now a lot of the teachers who do this kind of stop there, because what we're really looking for is where do the rays intersect, in this case the red and the green one. But there is additional rules to kind of make this a little more accurate. For rule 3, we could draw a ray starting from the top of the object through C and then back upon itself. So let's see what that looks like when we draw it out. So through C and then back to itself. Notice that see, it's just a little different, but it gives us just a touch more accuracy if we were to do that. So where those 3 lines intersect, or just 2 if you only do the first 2, that is going to be the location of your image. And yeah, it's below the principal axis, and that's important information. We can draw a little arrow here to kind of mimic the object that we've drawn, and we can see the arrow is pointing down. It's pointing down. That tells me, follow my cursor here, is it inverted or right side up? Question 3, the answer is inverted. It's the opposite direction. Question 2, is it enlarged or reduced? Well, you're really just comparing the relative sizes of these 2 arrows. The image arrow is obviously smaller, so this image produced would be reduced in size or smaller. And obviously it's on the same side as the object. So what do you think? Is that a real or a virtual image? If you said it's a real image, you're correct, because we could project this. I could put this object, let its reflection come off this mirror, and it would be projected onto a screen. Now, if we didn't want to draw these ray diagrams, they're a little tedious. We can just use straight up math. So here's the equation we get. It's the mirror lens equation. You can use it for mirrors or lenses. It looks a little weird at first, I understand, but it's not that bad. So here's what a little acronym I have to help you remember this one. I call this equation, if I do, I die. Look at it again. If I do, I die. For some reason that sticks in the head, and it's not that bad. So the if I do, I die equation. Let's work through a real quick example using the if I do, I die equation. So we can see it's made up of the focal point, the focal length, the DO is your object distance, and the DI is the image distance. So reading the problem here, assume that you have a concave spherical mirror, has a focal length of 10, centimeters. Locate the image for an object distance of 25. So what this means is I'm going to put an object, whatever it is, 25 centimeters in front of the mirror, and I just know the mirror has a property of this focal length. So subbing into the equation, 1 over 10, that's my focal length, equals 1 over 25, and then I'm just going to use some algebra and solve for DI. One thing students do mostly when they solve these problems is forget to take the reciprocal. When you find DI, it is going to be on the bottom, so you need to turn it over. And if you do that for this problem, you get 16.67 centimeters. I'd hit pause right here and I would run through the calculation yourself just to make sure you can do the algebra. So let's dissect this number here. We got a positive number coming out. And since the image distance is positive, we know this is a real image. It's on the same side. Its position is on the same side of the mirror as the object. What about the size and orientation? Well, we have a separate equation we can pull out. We call this the magnification equation, and really it's just a ratio. So it's not a lot of plugging and chugging, it's just a simple ratio. We can do one of two things. I can take a ratio of the image distance to the object distance, but my catch is I have to put a negative sign in front of that one. It's Dido. We call this the Dido, if that's a little reference to some Roman mythology, I think. Or maybe she was the mother of Romulus and Remus, I don't remember, but Dido. Or we could take a ratio of the image height to the object height. Now that comes from the ray diagrams. So from the if I do, I die equation, the information you're probably going to have is Dido. But again, don't forget your negative sign. So in the problem that we just worked, let's see, where did I have this one? Nope, not there. So in this one, my DI was 16.67. My object distance was 25. So without plugging into a calculator right here, it's about 0.65 or something like that is the ratio. And of course, it's negative, so negative 0.65. What that tells me is if it's negative, and it is here, the image is inverted. We saw that on a few slides ago. We typically get inverted images here. If the magnification is greater than 1, it's enlarged. Well, we got like a 0.65, so that means we're here. The magnification of our object was reduced. It shrunk. If you happen to get 1, that means it's the same size. That's what you would always get in a plane mirror. So here you see the calculations for ours. I was a little off. It was actually negative 0.67. So inverted and reduced. One more example, and then we're going to shut this particular lesson down. All right, assume a certain concave spherical mirror has a focal length of 10. Locate the image for an object distance of 5 and describe the image's characteristics. So why don't you hit pause, try this out, use the equation, see what you get, and then give me real or inverted, give me real or virtual, upright or inverted, or give me smaller or larger. All right, so after plugging in, I hope you got negative 10. That's an interesting number. That's the first time we've got it. What does that mean? That means if you plug into the magnification here, the negative signs cancels, and we get a large image. Okay, a large image. And since it was also a negative, it's virtual. This image showed up on the opposite side, or it's like behind the mirror. It was 2x, so it's enlarged and upright because it was not negative, positive 2x. So now we've got all this information. Let me go back. I just want to point out one thing. In the previous example that we worked, the object was placed on the outside of the focal length. The focal length was 10. We put the object on the very outside here, 25 centimeters, pretty far away. On this latest example, the focal length was 10, but I put the object really close to the mirror, within the focal length. And when you put the moral of this story is here, where you put the object in reference to the focal length determines what kind of image you get out. You don't always get the same type of image with these mirrors. Again, it's determined by where you put the object in relation to the focal length. So it's important to summarize this stuff right now. So for concave mirrors that curve inward, we may get a real or virtual. It just depends where they are. So I'm going to go through here and give you some scenarios. I suggest you take this down in a bit of a summary table so that you can reference it. If you're ever taking a multiple choice test on this, this is the most likely question you're going to get. Here's my mirror. First of all, it's concave or convex. And now depending on where the focal length is and where the object is, you have to communicate that you understand what kind of image you would get. So again, fill out your summary table as we go through it. So first of all, here I have a concave mirror. We're going to put the object in front of the focal length or between the focal length and the mirror. And we can see that when we get that, the image we get is virtual, magnified, and upright. If I move the object back in scenario 2 to put it between the center of curvature and the focal length, my image now comes back to the other side and it's a real image. But now it's upside down and it's slightly larger. Not much, but slightly larger. If I move that object to be exactly at the curvature, center of curvature, I get a real image that's inverted, but it's the same size. So that's a very special location to be at, the center of curvature. If I take it beyond the center of curvature and put an object very far away, then I'm going to get our initial scenario of a real image inverted and a little smaller. Now, an even more special location to put the object is at the focal length. We call that a blind spot. That is an actual blind spot that you have in some mirrors. You can see here from the ray diagram that these rays will never converge. So by putting an object at the focal length, that distance, you get a blind spot. No image is ever formed. All right, well that's our rundown of reflection, and as it applies to mirrors or any object that reflects a surface, we count that as a mirror. So complete your chart there. Go through this again, watch those last few slides, and get your summary. And reach out if you have any questions.